Now, leads is another very important, aspect of, interpreting the ECG. So, in the normal ECG, you have basically 12 leads, and what these leads are basically doing is that they're giving us, an image of the heart, from a different angle, right? So it's like, if you look at this whiteboard eraser, we can look at it from this angle, and then you can look at it from this angle, you can look at from this angle. So with every angle, it's giving us a different kind of a representation, right? So similarly, the heart, we like to look at the heart from different angles. We like to look at the electrical activity of the heart from different angles. So the heart is basically, it's not a 2D structure, it's basically a 3D structure, right? And it's a 3D structure with different sides. And so perhaps one comparison of the heart could be made to this box right here. So the heart has its borders, so like the box, there is an inferior border of the heart, which is right down over here, right? And then there are certain leads, which are actually telling us about this inferior border. So if there's something wrong with this inferior border of the heart, we have a certain group of leads which will detect that, right? And we call those leads as the inferior leads, right? And those leads are basically lead 2, lead 3, and then we have a lead AVF, right? So these are our inferior leads. So sometimes a person can have a myocardial infarction, and the myocardial infarction could involve either the lateral wall or the anterior wall, and in many cases it involves the inferior wall. So in order to see whether the inferior wall is affected by the myocardial infarction, we look at these inferior leads. So just like the inferior border of the heart, there is another border which is on the lateral surface of the heart, right? So this border over here is the lateral border of the heart, right? So just like the inferior border, the lateral border also has specific group of leads which actually tell us whether there is something wrong with the lateral side of the heart, right? So and those leads are basically lead V5 and V6, and then we have some other leads known as AVL and lead 1, right? So after the lateral and the inferior leads, then we have this part of the heart which is facing towards us, facing towards the chest. And there's again there are some leads which will actually tell us about the border which is anterior, right? So the anterior border, which is this, has its other kind of leads, and those leads are basically the anterior leads. The anterior leads are V2, V3, and V4. So there's another lead which actually tells us about the septum of the heart. Now we know that the heart has the septum, which is actually divides the right side of the heart from the left side of the heart. So many times what can happen is that this septum, which is right in the center, it can become infarcted. There can be something wrong in the septum, and so we have two leads, V1 and V2, and we call these as the septal leads, right? So these septal leads will actually tell us whether there is something wrong with the septum. Now if you want to know about the limb leads, imagine that you have a pizza in front of you, right? And a pizza usually has 8 slices. We're going to rub these two lines, this line and this line, right? And the lines that are left are limb leads, right? So easy mnemonic to learn these limb leads is left 12 for 3 rupees, right? Remember this mnemonic. Now left is referring to a lead which is known as AVL, right? AVL is representing the left. 1, 2 is representing leads 1 and 2. lead 1, lead 2. 4 is representing, the F in the 4 is representing AVF. 3 is lead 3 over here, and then the R in rupees is representing a lead known as AVR. So in summary, you should have a basic idea where these leads are placed and at what axis of the heart these leads are actually looking on. Now the other thing that you should know when you're looking at the leads is that you have to tell at what angle the electrical activity of the heart is. So normally what happens is that the electrical activity of the heart is going from in this direction, right? So when we draw the normal vector of the heart, so it's somewhat in this direction, right? And one of the best leads to actually see the direction of the electrical activity normally occurring in the heart is this lead 2, right? Okay. So but sometimes what can happen is that this electrical activity which is going like this towards lead 2 can actually just due to some reasons what can actually happen is that this electrical activity can actually change, right? So for example in some cases what happens is that the electrical activity might change to this side, right? And if it changes to this other side, the way you can actually tell whether the electrical activity has changed is that you will actually see a greater electrical activity in these leads, right? And you will see comparatively less electrical activity in these leads. So the leads in which the electrical activity is going towards will actually show a greater deflection. Right now when it comes to these leads, what happens is that in a normal ECG this is the wave pattern. You have a P and a QRS and the T wave after that. So what happens is that how we can actually tell in which direction the electrical activity is actually moving towards is by looking at these tall QRS complexes. So if for example this is lead 2 and for example this is lead 3, so we can actually tell that the electrical activity is more towards lead 2 and less towards lead 3. So the electric activity is somewhat like this. However, if the opposite situation occurs in which lead 2 becomes somewhat like this and lead 3 has this tall QRS complex, that is actually telling us that the electrical activity is now shifting towards lead 3, right? And similarly we have these other leads like AVR. Sometimes the electrical activity might shift towards AVR, right? And so these leads might show a more positive kind of a deflection, right? Sometimes they would shift towards AVL, and so AVL will actually show more positive deflection. Those leads which are opposite to AVR like lead 3 will show a very a very negative kind of a deflection. Now this situation happens AVL is showing a positive deflection, lead 3 is actually showing a negative reflection. That just means that the electrical activity is moving towards AVL and away from lead 3, right? So this is how we can actually tell where the electrical activity is going, and this is known as the axis, right? So if the axis is in most cases the axis is normal, but in some cases, in some abnormal cases, what can happen is that the axis might change, and when it changes from its normal axis, we call this as axis deviation, right? Now there are many causes of axis deviation, right? Sometimes the electrical system in the heart can have a problem, like for example in left bundle branch block or right bundle branch block, we can have an axis deviation. Sometimes what can happen is that the heart muscle it hypertrophies, it increases in its size, and so what happens is that if there is more muscle over here, there will be more electrical activity over here, so the axis will actually shift towards this side. If there is more right ventricular hypertrophy, the axis will actually shift towards the other side, right? So hypertrophy and bundle branch blocks, or basically problems in the conduction system of the heart, can actually cause axis deviation commonly. Now at a beginner level, you should just know about how to tell whether the axis is normal, how to tell whether there is a right axis deviation, RAD, right? How do you tell whether there is a left axis deviation, and how do you tell whether there is a extreme right axis deviation, right? So these are at the basic level, you should just know how to tell these three. Now, how do you know whether the axis is normal? It's very simple. You have two leads. One is lead 1. You can see, this is your pizza and this is lead 1. And then this lead which is going right downwards is your AVF. Lead 1 and AVF. So, if these two leads, are positive, that means that the electrical activity is closer to these leads. If both of these are positive, we say that the axis is normal. Because if both of these are positive, the only thing that can be possible is that the electrical activity is somewhere in between the two leads, right? And so we say that the axis is normal if both 1 and AVF are positive. What do I mean by positive? I mean that both of them are showing a QRS complex which is up, right? So 1 AVF QRS complex up, we say that the electrical activity is in the normal axis. Now the other situation can occur when AVF becomes negative, right? So if AVF is becoming negative, what is it showing? It's showing that the electrical activity is going away from AVF. So it's going away from AVF. 1 is positive, AVF is negative. uh, 1 is positive, we know that the electrical activity is near lead 1, but because it's away from AVF, we say that this is a left axis deviation, right? So 1 and AVF, 1 is up, AVF is down, we say that this is a left axis deviation, right? 1 is up and AVF is down, right? This is a left axis deviation, right? Now how do you tell whether there is a right axis deviation? The opposite will occur. 1 will be down and AVF will be up. So what this is telling us is the electrical activity is near 1, but it is away from near AVF, but it is away from lead 1. So it's somewhere in this axis, right? This axis is the right axis. So there is a right axis deviation, right? Now in some instances, what can happen is that the electrical activity can be in this axis, right? Now this is the right axis deviation if the electrical activity is over here, and if the electrical activity is moving towards this direction, we call this as the extreme right axis deviation. And in this instance, what will happen is that both lead 1 and AVF will be negative. Now at the basic level, it's just okay to know whether a person has a right axis deviation or a left axis deviation or an extreme right axis deviation. But at an advanced level, it's important to actually know the exact axis in terms of degrees, right? And that's important because a lot of diagnosis, like for example diagnosing hemiblocks, basically depends on knowing the exact axis of the heart, right? So the first thing that we need to know is that we need to know the axis of the individual leads in the ECG, right? And in order to determine that, we need to use a protractor. So I'm just going to give you a little idea of the individual angles that these leads are making, right? So lead 1 is actually making an angle of, as you can see, 0 degrees, right? Lead 2 is making an angle of 60 degrees. If you keep our protractor like this, we can actually find that out, right? And lead AVF, which is right, perpendicular, is actually making an angle of 90 degrees, which you can see here. Now you can see that okay, this is not that accurate, but you need to just remember is that lead 3 is making an angle of 120 degrees, right? Similarly, if we sort on the other side, we will have a minus. The degrees will be in minus because they're going on the other side. So AVL actually makes an angle of minus 30 degrees, while AVR makes an angle of minus 150 degrees, right? So basically you just need to have an idea of the axis of these individual leads, right? Minus 30 AVL, lead 1 is 0, 60 for lead 2, AVF is going to be 90, 120 for lead 3, and minus 150 for AVR. Okay, so once you know these individual axes of these leads, the next step is that you should look into your ECG, into the the limb leads, and you should see the most isoelectric lead. What do I mean by isoelectric? Well, isoelectric means that a lead which has equal amounts of its QRS complexes which are above the axis, and equal amounts which are below the axis, right? The upper part and the lower part, if they are equal, we call this as a isoelectric wave, right? So you have to look at those leads which are actually which is most isoelectric. So you'll have some leads which are in which there's just a lot of positivity, and then there are some leads which will be there's going to be a lot of negativity, right? So you're actually looking for the most isoelectric lead which has equal amounts of positivity and equal amounts of negativity. So for example, in the 12 lead ECG, what we see is that we find that lead 2 has this kind of a waveform, and it's the most isoelectric of all leads, right? So if we say that okay, lead 2 is the most isoelectric lead, then what this is actually telling us is that the axis is now 90 degrees to lead 2. So 90 degrees to lead 2 can mean it could be here, or it could be somewhere here. It could be on either sides, right? So in order to know what is the angle at 90 degrees to 60, either you add 90 to 60, which makes it 150, or you subtract 90 from 60, which makes it minus 30. So either the axis is 150 plus 150, or the axis could be minus 30 if lead 2 is most isoelectric, right? Okay, then the next step is obviously you have to, the axis can only be one, either it's minus 30 or it's plus 150. I wish this is not complicated, right? So in order to know which of the two axes is more correct, you'd look at other leads for reference. For example, if you look at AVL, and AVL is actually showing you something like this, and at the same time you're looking at lead 3, and lead 3 is showing you something like this, right? So you can easily say that the axis is towards lead 3, so it's on this side. If lead 2 is isoelectric, it's on this side. So the axis in this case is round about minus 30. So that's how you can actually very accurately say that what, the axis is minus 30. Then similarly, let's take another lead to be isoelectric. So let's just assume that AVF is now the most isoelectric lead, right? So AVF is showing equal amount of positivity and negativity. So we can actually say that now the axis is going to be either it's going to be on 0 degrees or it's going to be on 180 degrees, right? How to determine that? We look at the leads. We look at lead 1. If lead 1 is showing positivity, and here we don't have any lead which will actually show us the opposite of lead 1, so we'll have to make a guess from AVR, right? So if AVR is actually showing some negativity, then we can actually say that the axis is towards lead 1. So the axis in this case is going to be, if AVF is the most isoelectric, the axis is 0 degrees or near 0 degrees. Now this is something which requires a bit of estimation as well. so you're basically using the corresponding leads, and you're trying to estimate what the exact axis would be. Okay, the other thing that you need to know is that many times what happens is that when you're looking for an isoelectric lead, you usually don't find a lead which is completely isoelectric. Sometimes you would find a lead which is like this. So this has a little more positivity, and the negativity is a little less, right? So this is not completely isoelectric. And for example, if this is lead 2 and it's not completely isoelectric, you know what we can say is that the axis is towards 90. Yeah, so what we can actually say is, if this is sort of it's more positive, then it's not completely at a 90-degree angle. It's because it's more positive, so it might be at 80 degrees to lead to. So this might be at minus 20, right? Or on the other side, something like 140, right? And then what we can actually do is that, in order to determine the axis accurately, we can actually look at other leads for reference, right? For example, in this situation, what we are saying is that maybe the axis is not, it's not minus 130, but it might be minus 20. So when we look at AVL, if it is exactly minus 30, AVL will be fully positive, right? But if it's less than minus 30, if it's minus 20, then AVL will actually be positive, but it might have a little bit of that negativity also. So if AVL is fully positive, then minus 30 might be the axis. If AVL has a little bit of a negativity, then minus 20 degrees would be the estimation of the axis, right? So this is how we can very accurately determine what the right axis is in terms of degrees. Now the other thing that you need to know is that what is the normal axis of a person. Now a lot of people would think that, okay, this quadrant is the normal axis, but that's not quite true. The normal axis is actually somewhat from this line, which is 90 degrees, not to 0 degrees, but a little bit towards minus 20 degrees. In some books they go up to minus 30 degrees as well. So anyways, I like to use the range of minus 20 degrees. So from 90 degrees to minus 20 degrees is the axis, the normal axis for a person. In some very young adults, what can actually happen is that their axis could be minus 20 degrees, but that could also be normal. So all this part, from 90 degrees to minus 120, minus 20 degrees is supposed to be, the normal axis for a person. So as long as, the electrical activity of the heart is following, in this direction, the axis is normal. So the other thing that is important regarding these leads is where these leads are actually placed, right? So if you actually look at a human model, what we will see is that basically we have, when it comes to the limb leads, basically there are 4 sites where these limb leads are actually placed. So you have a clamp like thing that you sort of attach, you open it up and you attach one on the left leg, one on the left arm, one on the right arm, and one on the right leg. And basically this clamp like thing, it has different colors. So one of the ways which we can actually use in order to learn the colors is, we should know about the traffic lights. Right, now the traffic lights are red, yellow and green. Red gets attached to the right arm, right? So red clamp will come over here, right? And then you have the second traffic light is yellow, so the yellow clamp will get attached over here. So it's going in a clockwise fashion. Right arm red, yellow clamp will get attached to the left arm, and then you go downwards, and you have the third traffic light, which is green, so the green clamp will get attached to the left leg, right? And then there is another clamp which is black in color, so the black clamp gets attached to the right leg. So the other thing you need to remember is that in different hospitals, perhaps the coloring scheme might not be like this. It might not be red, yellow, green, black, and even these clamps might even be different. So it's also important, usually if you have a clamp, they will have a label on it. So if the clamp is actually it has right arm written on it, then then the right arm is the place where it needs to get attached, right? So the coloring scheme is important, but you should not completely rely on the coloring scheme, because it may differ. Now the other very important question is that just by attaching these clamps, how are we getting this kind of a thing? How are we getting these 6 different kind of representations just by the limb leads? So in order to understand that, what we need to do is we need to understand what we're actually trying to do over here. So what we're basically trying to do over here is, when we put these electrodes, is that basically in an ECG what we're doing is we are measuring the voltage, right? And we're actually comparing the voltage from two different parts. So sometimes it's comparison between the right arm and the left arm, sometimes it is a comparison between the right arm, the left leg, sometimes it's a comparison between the left arm and the left leg. So for example, if there is a greater difference between the right arm and the left arm, what it will actually show us is that will show us great positivity, right? And the right arm and the left leg, it is represented by lead 2, right? The right arm and the left arm is represented by lead 1, and the left arm and the left leg is represented by lead 3, right? And this is what can sometimes be represented by something known as the Ovince triangle. So in the Ovince triangle, we have a comparison made between the right arm and the left arm, and that's lead 1. Comparison between right arm and left leg is lead 2, and the comparison between left arm and left leg is actually lead 3. So this is how we actually get the leads. Here it's also very important to understand the concept of voltage, because sometimes this can be confusing. And basically in an ECG we are basically measuring the voltage, and if you even see the readings, it's in millivolts. So basically voltage is just it's basically a potential difference of potential. So for example, you have a battery over here, and the battery says that it's actually a 10-volt battery, and then there is another battery which is a 20-volt battery, right? So if I would ask this question, that which of these two batteries is a stronger battery, you would go for battery number 2, because it has 20 volts. And in basic terms, what it means is that there is greater separation of charges over here, so that's why this is a stronger battery. Now in electrophysiological systems, uh, potential is a very important thing, right? What is potential? For example, you have a slope, right? And in this slope there is a ball over here. Right now, because of the slope, the ball will actually move downwards, right? Then you have another slope, and this other slope is even more steeper, right? And in this slope, the ball will actually move with even more greater velocity, speed, right? So the second example was the example of this battery. There is a greater potential difference, there is a greater separation of potential, so the ball will move, or the current will move quicker as compared to this one, where there is less difference of potential. So what we are doing in this ECG is basically we are measuring the difference of potential, and by using this difference of potential, we are getting recordings on our different leads. So for example, if you consider lead 2, we have one pole which is on the right arm, and then there is another pole which is on the left leg, and we have a voltmeter, and in this if there's an electrical impulse which is going towards this direction, what will actually happen is that it is going towards this electrode and it is going away from this electrode. So lead 2 will actually show a positive deflection, right? This is what is basically happening with lead 2, right? With lead 1, in another example, if you look at lead 1, in which there's one electrode at the right arm and the other electrode in the left arm, and we have a voltmeter which is actually telling us the potential difference, and you have a wave which is actually going now in this direction. So what will happen is that on the ECG, what you will see is, you will see a positive deflection if the electrical activity is going like this, right? If the electrical activity actually starts to go in the opposite direction, in this direction, then what you will actually see is, you won't see this, but you will see the opposite. You will see something of this nature. It will be negative. Similarly, with lead 2, this also occurs. If the electrical activity is going in the opposite direction, from the left leg to the right arm, then rather than seeing this, what you will see is, you will see a negative deflection. Right? So this is how these leads are actually helping us determine where the electrical activity is going. But then there is another third scenario as well. Sometimes what can happen is that, for example, in lead 1, the electrical activity, rather than going here or here, it's actually going in a perpendicular axis, right? It's going like this. So if the electrical activity is going in the perpendicular axis, then either you will see very little deflection, something of this sort, and so it will be equal positivity, equal negativity. So this is something which is known as, this we can call this lead as isoelectric, right? So if this lead is isoelectric, it means that the electrical activity is going perpendicular to the lead, and this phenomena can actually be used to calculate the axis, and this is something which we have previously discussed. So you've wondered that lead 1 and lead 2 and 3 are not the only 3 limb leads that we have. We have other leads as well, right? So in summary, there are basically 12 leads, and some of them are the limb leads, which we've discussed in detail, and then there's some leads which are known as the chess leads, right? V1 to V6. Right now, when it comes to the limb leads, we've discussed 3 limb leads: lead 1, lead 2, lead 3. Right? These are known as the bipolar leads. Right? Why are they called as bipolar leads? Because they are actually giving us a recording between 2 poles. Right? So the voltmeter is there, and you have 2 places, and it's basically comparing the recording between the 2 places. But these are not the only leads. Right? There are other leads as well, which are known as the augmented limb leads. Right? Augmented limb leads. Augmented means that they're modified. Right? And these 3 are AVL, AVR, and AVF. So how are these augmented limb leads working? So if you look at the Ovince triangle, and you have the right arm, left arm, and the left leg over here, what the augmented leads basically do is that they they actually take the sum of 2 of the 2 places where our electrodes are attached, like for example the right arm and the left leg. They will take a sum or an average of these 2, and they will actually compare that with the third one, right? So it becomes like this. If you want to take the average, we can actually take a midpoint between the 2, and from this the comparison of electrical activity is made by the the other place. So we can have a augmented limb lead in this direction, right? The augmented limb lead in this direction is known as AVL, right? And AVL is oriented at about minus 30 degrees towards this side, right? And then similarly, if you take the sum of these 2 points, and you compare it with this point, you can get another lead, right? And this is known as AVR, right? This is another augmented lead, AVL, AVR, right? So, and then you have another limb lead that we can actually get by taking the sum of the right arm and the left arm, and comparing it with the left leg, the left leg, sorry, right? And so we get another uh, lead, and this lead is known as AVF, right? And AVF is oriented right downwards, at an angle of 90 degrees. So in this way, what we've got is that just by attaching electrodes at 4 points, we can actually get 6 different angles, 6 different leads, by which we can actually visualize the electrical activity. Now we've done all the electrodes, but you might have wondered what's the purpose of this electrode over here, right? We know how the Ovince triangle is actually constructed, using these three electrodes. But then what's the purpose of the right leg electrode? Well, this electrode basically acts as a ground. So it basically gives us reference to 0 volts. uh, you know uh, right. So moving on, let's do the chest leads, right? So we know what the limb leads are, and now we have another representation that is actually shown by the chest leads. So if this is a box, and the box is actually a 3D structure, and so is the heart. The limb leads is basically what the limb leads are doing is that they are giving us, a representation, in the downward direction, uh, but they're not giving us, a representation, in the outward direction. So they're giving us a representation downwards, upwards, uh, in more of a 2D axis, but they're not telling us about the electrical activity that is coming outwards, right? And in order to know that, we need to take help from the chest leads. So the chest leads are actually telling us about a outward axis orientation, right? So if this was a person, and if I cut him, from on top, and I was looking at his heart from the top, what I would actually see is I would see something of this nature, right? I would see his heart in his chest cavity, and at the back, he would have the vertebrae. In the front, the sternum would be present, and now I have these leads which are actually giving me the electrical activity in the outward direction, in another plane, right? The limb leads were actually telling us, the electrical activity only in this kind of a plane, right? But it wasn't telling us the electrical activity in the outward plane. So in the outward plane, we use the chest leads, right? So we have 6 chest leads that we use. We could use more than 6 leads as well, uh, but conventionally we use these 6 leads: V1, V2, V3, V4, V5, and V6. So for example, a person has a myocardial infarction in the anterior wall. Right now the anterior wall is somewhere over here. Right, this is the anterior wall of the heart. Right. So in this situation, in this situation, using just the limb leads, cannot tell us anything. Right. We need to look at the chest leads, because the anterior surface is represented by these chest leads. And so many times in V3 and V4 you will find changes. Even in V2 can also be used for changes in the anterior wall. Then sometimes what happens is that the person could have there is another wall which is known as the lateral wall. So person could have an MI which could involve the lateral wall, right? And the leads we look at to find whether the lateral wall is infarcted is V5 and V6. We can use other leads as well, like AVL and lead 1 as well. but we also use these two leads. And many times what happens is that the person doesn't just have the lateral wall or the anterior wall, but has a mix. There is the anterior wall is also affected and the lateral wall is also affected, so you see changes in the anterior leads, and then V5 and V6 will also show changes. So in this kind of, if this was a myocardial infarction in which there was changes in the lateral leads V5 and V6 and the anterior leads, and so we would call this an anterior lateral myocardial infarction. Now in some cases the right side of the heart could be affected, the right ventricular myocardium could be affected. And if you want to see where there's a problem in the right myocardium, we look at these three leads, V1, V2 and V3. These three leads can tell us if the right side has a problem. Then in some patients what can happen is that the septum, the basal septum, so in some patients what can happen is that only this part, which is known as the basal septum, this can become affected. And if the basal septum is affected, you will see changes in V2 and V3, right? So these are certain patterns why we can actually detect using these chest leads. And in some situations what can actually happen is that the person might have a infarction of the posterior wall, which is somewhere over here. Right now you can actually see that we don't have any leads which are actually telling us about the posterior wall, so we can actually attach some other leads known as V7 and V8 to the posterior, and these actually leads can actually tell us about a posterior wall infarction. We can get a hint from a posterior wall infarction is if you look at the anterior leads, and in the anterior leads we find some changes which are a reflection of a MI. There are changes which are opposite that that you normally find in a myocardial infarction in the anterior leads. If you find such changes, then you might think that maybe the posterior wall is getting infarcted. So the anterior leads can actually give us a hint that that we should look and place more leads and look at the posterior wall. So now it's important to know how these leads are actually placed, right? So if this is the manubrium, and you have the sternum, this is the xiphoid process. So you have this thing which is known as the angle of Louis, or the sternal angle, and on the sternal angle we have the second rib which is attached. Right beneath the second rib we have a space which is known as the second intercostal space, right? So the second intercostal space is very important because from the second intercostal space we move downwards and we go to the fourth intercostal space, the second rib, third rib, fourth rib, and beneath the fourth rib we have the fourth intercostal space. Right now on the fourth intercostal space towards the right side, this is the right side, so you will actually put V1 over here. On the left side you will put V2, right? And then what will happen is that you will actually beneath the fourth intercostal space you have the fifth intercostal space, right? Second, third, fourth, fifth, and this is the fifth intercostal space. And what you will do is that you will find the mid clavicular line. In the center of the clavicle you will find the mid clavicular line in the fifth intercostal space. And let's just assume that these spaces, these ribs are moving like this. So in the fifth intercostal space we will, in mid clavicular line, we will attach another lead, and that is going to be our V4, right? So V1 was here, V2 is here, V5 is here. This is the point where the apex of the heart is felt, mid clavicular line, fifth intercostal space. Then between V2 and V3, right in between, the midpoint, we will attach V3. So V1, V2, V3, V4. So then, moving more towards the left, we have the axilla, and the axilla forms a line which is known as the anterior axillary line, right? So at the anterior axillary line we will then attach V5, and in the mid axillary line, which is more leftwards, we will attach V6. And this is how we attach these 6-limb leads. So we have some other leads as well, V7 and V8. These are our posterior leads that we sometimes can attach if you are suspecting a posterior MI. And as we said, that V5 is attached in the anterior axillary line. Similarly, there is a posterior axillary line, and in the posterior axillary line we attach V7, right? And then there is another lead known as V8. So V8 is actually, this is the scapula. There's a line which sort of passes through the scapula and the inferior angle of the scapula, and this line is known as the scapular line. So on the scapular line, we will attach V8, and this is at the same level of the 5th intercostal space.